All right, this is my project assignment 1, just looking at CubeSats and rotation wheels. So the information that we're given is we're told that our CubeSat is a 10 by 10 by 20 rectangular prism, as you can see on my paper. And then what that tells us is that the radius of our rotation wheel has to be less than 5 centimeters, because that's the radius of the box if it's at the center of the rectangular prism. So the way a reaction wheel works is that it rotates inside of the CubeSat, and so say it's rotating clockwise, it's going to cause the CubeSat to rotate counterclockwise. All right, so going on to question 1, we're asked to estimate the moment of inertia around each axis. So I'm going to be looking at the z-axis, because from analyzing the z-axis specifically, we can form an equation around with which we're able to analyze the inertia in general. All right, so we have our inertia equation as a triple integral, taking into account density and the volume, because the volume can be indicated as the integral of dx, dy, dz. So that's the 3 side lengths indicated as A, B, and C. So they each correspond to one of the axes. So that integral represents our volume. So say A corresponds to the x-axis. So if we're going from the origin of the CubeSat, negative a over 2 is one side to a over 2, which is the other side. So that just is the bound is the whole side length. So then if we analyze this big integral, we are able to pull out the dz integral, and just because that's a constant, it's going to be constant side length c, because c corresponds to the z-axis. So we're left with c times the density, which is also a constant, so it can be pulled out. And then we have integrals in terms of dx and dy, which we can analyze. You can look at this math closer. But as we get down, if we see here, we have the side length c times the density, and then we also have it in terms of side lengths a and b. And then how we're going to simplify this further is if we look at the density in terms of mass over volume, we get it as the mass over a times b times c, so all 3 of our side lengths. And that allows us to cancel out some variables, and that gets us to 1/12 times m times a squared plus b squared. And if we look up the known equation of the moment of inertia for a rectangular prism, that is indeed the equation. So we know we did that correctly. So let's move on. Okay, so for problem 2, we're just asked to design our reaction wheel. So for my reaction wheel, I decided to make it an apparatus of 3 interlocking rings. So they're able to rotate simultaneously to be able to turn the CubeSat in different directions simultaneously. So there's the biggest ring and then 2 smaller rings set inside of it, all connected to a central motor. So I decided to make my material titanium because it's pretty lightweight and it's heat resistant, which is good in space because one, the motor will get pretty hot, and yeah, just things get hot when they do things for an extended period of time. So having a heat resistant metal is a good idea so it doesn't get melted and do weird deforming things. Anyways, okay, so I have my 3 rings. They have 3 different radiuses. The largest ring is 4.9 centimeters because the radius of it is 4.9 centimeters because it has to be less than the 5 centimeters, which was our max radius because of the size of the box. And then I had the thickness of the rings as 2 millimeters, and then the width of each of the rings as 7.5 milliliters. I kept things pretty small just because you don't want bulky metal in there, just jamming up the apparatus. So then from those dimensions, we can find the volume, and then from that, we know the density of titanium, so we can find the mass of each of the rings, and that allows us to find the inertia, because the 3 separate rings are all going to have an inertia value, so we're able to find the inertia of the whole apparatus by just summing those. So if we go over here, we have our inertia equation, and we get that the inertia of our 3 rings is going to be 1 times 10 to the negative 4 kilogram meter squared. All right, and then problem 3, let me pull that up. It asks us in which plane the wheel should rotate to be able to rotate it 90 degrees around the x-axis. So to be able to do that, it's going to be rotating around the x-axis, obviously, and then the wheel is going to be in the y plane, and that's going to cause it to rotate around the x-axis. And then what is the angular acceleration of the reaction wheel in order to accomplish this maneuver? So with this, we know how much we want to rotate it. We want to rotate the CubeSat by 90 degrees, which is the same as pi over 2 radians. And then we know that we start at a velocity of 0. And how we're able to figure this out is because we want the CubeSat to speed up to a max speed and then slow down, so until it gets back to a velocity of 0. So this is the next question, but it's just a graph of the movement. So it's going to be this parabola shape for the velocity where it's at the max velocity at, if the full time is 45 seconds, it's going to be at its max velocity at the center. So when we're solving for the acceleration, we know that I just realized I made a tiny little mistake, because it's going to be half of our time. So where 90 degrees is pi over 2, it should be pi over 4 to account for 90 degrees. Yeah, because we need to see how far it's going to get in 45 degrees. So yeah, these numbers are going to be a little bit wrong, but the idea is there. Yeah, so if we do that calculation, we get the acceleration to be 0.0062 radians per second squared. And then we looked at this graph a little bit already, but we know that the, if we're looking at the key values, we know that the max velocity is going to be at 45 divided by 2 seconds. And we can find that using a kinematics equation and get that to be 0.1395 radians per second. And then finally to part D, rotational motion and power are related by the equation power equals torque times angular velocity. And then torque can also be written as inertia times angular acceleration. And we luckily have all of those values, so we can solve that. The max power is going to be when the motor is moving at its max velocity, which we found to be that 0.1395 radians per second. So if we plug in the known values of the inertia and angular acceleration and then that max velocity, we get that the max power our motor is going to have to do is 8.6 times 10 to the negative 8 watts. And that is the whole thing.